So good morning, everyone. My name is Yuandong Fan. I'm from Technical University of Munich. Today I'm going to present my paper, Automatic Creation and Enrichment of 3D Models for Pipe System by Co-registration of Laser Scan Point Cloud and Photos. So I know this kind of long title seems to be really confusing. Actually, when I wrote the paper, I also changed the title for many times, but I think this title, the current version, can describe what I put in the paper quite well. So actually, there are three main parts in this title. The first part, automatic creating and enrichment of 3D models. It is what we want to achieve in this paper. And the pipe system is it's the case study we made to show the method we use really works. And the co-registration of laser scan point cloud and photos is actually the novel idea we proposed in this paper. This paper is related to my PhD project, which is built environment digital twinning. What I have been doing in last years is that I try to create a digital model from the two different data sources automatically. So here also the two data sources are apparently the point clouds and the images. There are also two keywords here. The first one is why do we need an automatic creation method? You may have already heard in the previous presentation that currently the reconstruction process requires much human effort, which makes the cost to generate a model exceeds the benefits we can receive. And the second key point here is why do we need images? The most reconstruction previous work process, they use point cloud only, but we think we could use two different data sources. A more detailed model could be reconstructed because somehow we have the feeling like the point clouds and the images can provide supplementary information. In the normal point cloud reconstruction process, we could reconstruct the structural elements quite well. For example, wall, ceiling, and floor. Especially when we add the deep learning technologies, the whole process can be further enhanced. So, for example, here is the input point cloud we captured at our chair in the Technical University of Munich. And here's the color-coded segmentation result provided by deep learning. In this image, the different colors here represent different classes. Then based on the point clusters, the surface can be further extracted. Then we can fit a mesh model to those point clusters. So this process is pretty straightforward and it's fully automatic. But it really depends on the deep learning prediction. Qualitatively, we can see in the figure 1b, the prediction is pretty good. The blue points are ceilings, red are walls, and green are floors. If we look into the numbers as shown in this table, the KP-con with the deep learning model we used, these values are shown in mean intersection over union matrix. As we can see, all these numbers are around 90%. I would say these predictions are pretty good. But if we continue this table, for example, we want to reconstruct more elements, like small scale, but still very useful for the building maintenance element. The prediction by deep learning is not as good as for structure elements. As you can see, the numbers is worse. So then there are mainly two reasons, I would say. The first one is that the deep learning model is just not capable of detecting small or predicting small elements as good as the larger object. The other reason is probably the point cloud resolution is not high enough to detect these small elements. For example, the smoke alarm or the light switch on the wall, the depth or the thickness is pretty low. if we check into the point cloud, so if sometimes it's even really hard for humans to know this, to find these objects. So if human vision fails in this case, how can we expect computer vision works in the point cloud? So then we want to include images in this process because these small elements can be recognized well in images. In our previous work, we proposed this pipeline to combine the 2D and 3D reconstruction of detection together. First, we collect the laser scan point cloud and images in the same area building, then reconstruct a photogrammetry point cloud based on the images we took. And by 2D image segmentation, we can extract the semantic information from images. And by using the camera poses estimated by structure from motion, the semantic information from 2D images can be mapped into 3D space. As we can see, there are some point clusters of smaller objects. Then, as what we usually do for the structure elements, we just fit a mesh model to the point cluster of smaller elements. So now come to the topic of this paper. The pipeline we propose is nearly automatic, except for the step that aligns the laser scan point cloud and the photogrammetry point cloud. In our previous work, we did this manually. We just select 4 or even more points and align the photogrammetry point cloud and the laser scan point cloud manually together. But in this paper, we want to present a way to register those photos taken by cameras to the 3D laser scan point cloud automatically. So this step is mainly in this yellow box, so photogrammetry co-registration. As you can see here, we have 2 different input photos taken by camera and also photos taken by the scanner and point clouds taken by the scanner. Here's the machine we use to collect the data. It's a Leica RTC 360 laser scanner. This laser scanner can take photos as well and scan the 3D space at the same position. Then those photos taken by the laser scanner can be considered as a bridge to register photos taken by images to the 3D laser scanned point cloud. As you can see in these two, in the first images, it's the sparse point cloud with camera poses in the photogrammetric process. And these camera poses in the blue circles are the camera poses estimated by the laser scanners, and the rest are the camera poses of the image taken by the normal camera. And the right figure is the dense reconstructed photogrammetric point cloud. The registration of images of the images taken by camera to the 3D space is pretty good. For example, here is one photo taken in the ground floor or underground floor in our campus. And here is the visible points at the given camera pose, which is estimated by the photogrammetric process. As we can see, they matched pretty well, I would say. You can see here is the door frame here, and the visible points at the given camera pose, the visible points here, and even a door stand here, even a door stand here. I would say this registration process works pretty well. So then in our experiment, we showcase point clouds of several pipes to test how our combined 2D and 3D reconstruction and enrichment work. So we use these point clouds as our input. What we want to achieve is to extract those pipes and enrich the pipe models with some useful information. Then the deep learning is similar to the structure elements. The deep learning is also applied to predict pipe classes in the point cloud. In this image, the pipe classes is colored in green in yeah. Then the predicted points of pipes is further clustered into different instances using region group method. Here, different colors represent different pipe instances. Then ransack is applied to fit cylinders to different instance clusters. What you can see here is the cylinder axis computed by ransack. The starting and ending point of the cylinders are found by projecting points to the axis. Then we reconstruct the cylinders in FreeCAD. For elbows, we use the, Then we reconstruct the cylinders in FreeCAD. For elbows, we use the swag function provided in FreeCAD. So next, at last we map the information extracted from the 2D images to 3D model. This mapping process is introduced before, which is, I would say, the main contribution of our paper. First enrichment is the text information enrichment. Usually in our buildings, at least in the buildings in TUM campus, on those pipes there are usually some labels which shows the fluid properties, for example, fluid direction or fluid temperature or something like this. And by applying the text detection in 2D images, and then apply the text recognition, those kind of text information can be extracted in 2D images. And these extract 2D images can be further mapped into a 3D model. Here you can see these labels are actually in German, which means the Heizung-Vorlauf means flow and the Heizung-Rücklauf means return. The second image here illustrates that we found that if we, in the text recognition process, if we found the text recognition score is extremely low, we need to rotate the detected bounding box of texts to a horizontal position. Then we could really get a very high recognition score. So the second enrichment into the image is that we extract the shape of labels here. We just apply the simple edge detector to detect edges and determine those arrow direction. For those arrows, for example here, the arrow heads are always in the middle, and therefore we can determine this is the direction of this arrow, which also shows the direction of the fluid inside the pipe. Yes. Then we add the last step, or add the information extracted by the last step into the final extracted model. We can see the pipe instances, fluid direction, and also text information attached to the pipes. In summary, in this paper, the proposed automatic registration method provides the possibility to update the proposed automatic creation method provides the possibility to update the 3D models, or sometimes we can call it digital twins or scan-to-beam process with some lightweight capturing device. For example, if we want to create an accurate model, at the beginning we could use the accurate laser scanner to create a 3D model. But then if there is no significant change in the environment, probably in the updating process, we can just use very lightweight capturing device like our cameras or even with our handies to capture the 3D environment, and then run through the process, then change the information in the 3D model. Yes, that's it from my presentation, and I thank you so much for your attention.